So we showed, I think the first thing we showed was that if we have a connected domain and the derivative is a function which is analytic on the domain, the function is a constant provided either of the two cases. In either of the two cases, one is the vanishing of the derivative identically, and the second one is vanishing of all derivatives at some point of the domain, right? So this is sometimes called the principle of analytic continuation. The result that the function is a constant if the derivatives are all zero at some point. Okay, this is called the principle of analytic continuation sometimes for reasons that I will not go into now. There is something called analytic continuation, which I don't think we will be able to go into. And then we looked at the zeros of an analytic function and observed that the derivative, the zeros are isolated. The set of zeros doesn't have any limit point in the domain. All the while you assume that the domain is connected, okay, generally. As a consequence of this, we have the identity theorem, which says that if an analytic function vanishes on a set with a limit point in the domain, then the function must be zero. Or stated another way, if two analytic functions agree on a set with a limit point, then they must be identical. So this is a very strong result, right, for analytic functions, unlike smooth real functions. And then what? The maximum modulus principle, what we proved, and using the maximum modulus principle, we also, I think, proved the Schwarz lemma. Right? Is that all that we did yesterday? Okay, so to start with, did any of you notice that in the proof of Schwarz lemma that we wrote down, there was a cheating? Right? This was Schwarz lemma. Of course, there is something more about the derivative and conditional equality and so on. So, but this is a basic thing. So, how did we prove it? So, we define g of z and said we applied the maximum modulus principle for this. How did we do it? J is analytic and on the boundary it is less than or equal to 1, and therefore it is less than or equal to 1 the interior also. What was f? F is an analytic function on the open unit disk. So, to start with, f is defined only on the open unit disk and not on the boundary, right? Whereas, what did we do? We said on the boundary, mod g is less than or equal to 1 because mod fz is less than or equal to 1 and mod z in the denominator is 1. So, how do you get rid of this? Simple. You look at a smaller closed disk and apply the maximum modulus principle. Take R to be less than 1 and on mod z less than or equal to R, apply maximum modulus theorem. What do we get? On the boundary now, on mod z equal to R, f is defined, right? Because we are inside the disk D. So on mod z is R now, right? Fz over z, so mod. So which gives you, therefore, mod gz is less than or equal to R, 1 over R for all points in the interior also. By the maximum modulus principle, right? Apply to G. And therefore, mod f of z is less than or equal to mod z over R. But R is arbitrary, anything less than 1, right? So you can let R return to 1. So everything is fine now, right? For so if you like, take R to be 1 minus epsilon, right? So epsilon is arbitrarily small. So this is going to be true for given any z in the open disk, the distance is going to be something less than 1. So you can take any point z here, you can always find a disk which contains that, and therefore, so since r less than 1 is arbitrary, follows that by letting r to tend to 1. So the rest of the argument is essentially the same as before. Of course, the obvious question, once you have this lemma, is what happens when you drop that condition that f of 0 is 0. Okay? We'll come to that in a moment, a little later. But in the meanwhile, given an application of Schwarz lemma to determine all the automorphisms of the unit disk. What do you mean by automorphism here? Analytic diffeomorphisms. It is a bijective analytic map from D to D so that the inverse map is also analytic. Analytic automorphisms. First of all, there is a simple class of Mobius transformations which are automorphisms of D. Look at z minus a over 1 minus a bar z mod a less than 1. This is going to be analytic in D because the denominator vanishes only at 1 over a bar, which lies outside the unit disk because of this assumption. Okay? So phi A is analytic D. Does it map D to D? In fact, of course, it is analytic everywhere except at 1 over mod, 1 over a bar, right? So, in particular, in the unit disk. So, does it map the unit disk to the unit disk? What happens on the unit circle? On the unit circle, although it is defined actually, right? And mod z is equal to 1. What can I say about phi of z? That z bar is 1. That z bar is mod z square. So when mod z is 1, what do you get? It is 1. Right? This and this have the same modulus. Mod z is same as mod z bar, right? So phi A maps and therefore phi A must map the interior of the unit disk to the interior of the unit disk. Why? Maximum modulus theorem. So on the boundary it is 1, modulus is 1. So in the interior it has to be, modulus has to be less than 1. So phi A maps D to D is analytic, but is it an automorphism? Is the inverse, is it bijective? What about the inverse? We can straight away check that mod A is less than 1, modulus of minus A is also less than 1. So you look at phi of minus A, which means Z plus A over 1 plus A bar Z, right? That is the inverse of phi A actually. So this you can just write down and check, okay? That means evaluated at any Z, it's just Z, okay? And the other way also. Therefore, phi A has an inverse which is phi of minus A. Of course, we already know that phi of minus A is analytic, right? This phi A is analytic for any A inside the unit disk, so also for minus A. So this shows that phi A is an automorphism. This D is a group, of course, under composition. Take any real number alpha and just multiply by e power I alpha here. Okay. So the constant of modulus 1. So obviously, these are also automorphisms of D, right? Just multiplying by a fixed constant of modulus 1. What we want to say is that these are all the automorphisms of D. That is, any automorphism of D is of the form phi A alpha for some A modulus A less than 1 and some real alpha. Every automorphism of D is of this form. So start with an automorphism of D, then we want to show that. So in particular, F is analytic from D to D. Look at the image of 0 under this automorphism. It may be 0, it may not be 0. Call it something. And of course, mod A is less than 1. We want to use Schwarz lemma now. But Schwarz lemma cannot apply to F directly because we need the condition f of 0 is 0. Here we don't know what f of 0 is. Maybe 0, may not be 0. So you have to get, starting with f, you have to get something which maps 0 to 0. Right? So define look at what this phi a does here. What does phi a do? It maps a to 0. Right? So your f here maps 0 to a, and you have something there which maps a to 0. So if you take the composition, that's going to map 0 to 0, analytic on D, right? So you can invoke Schwarz lemma. So take the composition of, let's call it G. Check whether the order is right. You want 0 to go to 0. So what is G of 0? It is phi a of f0. F0 is a, phi of a is 0. So things are fine, right? Then mod gz is less than or equal to mod z, right? Schwarz lemma applied to G. What more can you say about G from Schwarz lemma? What about G inverse? G is an automorphism, right? F is an automorphism, phi A is an automorphism, so G is an automorphism. So the inverse also maps D to D analytically. What is G inverse of 0? 0, right? So you can apply same argument with G inverse in place of G. Okay? So since G inverse also analytic and G inverse 0 is 0, we can also apply Schwarz lemma to G inverse. So the two together give you what? If you write W equal to G of Z, then G inverse W is Z. Okay? So what does this give you? G inverse Z is, so okay, write W here instead of Z. So what do you get therefore? So maybe you can write W here and W here so that there won't be any confusion of notation. So this is Z and that is G of Z. For all Z. We already had the reverse inequality, so we conclude that mod Gz equal to mod Z. Now what? Equality holds in the Schwarz inequality, the Schwarz lemma, right? So what is the conclusion therefore? Equality holds for some non-zero Z in Schwarz lemma, then the function must be some e power a alpha Z, right? So condition for equality in Schwarz lemma implies Gz is a rotation for some real alpha. Phi A, are we getting what we want or there is a change that we have to do? Let's see. So what does this give you? Phi A composed with F is just multiplication by e power a alpha. So what is F? Do we get it all right? Or? Probably we should take F inverse there. Let's see. Yeah, I think to get it in this form that we had written. Yeah. Probably we have to take F inverse here. See, just write out and see. You don't get this form, right? So this is what we want to get, e power I alpha into z minus a on minus a bar z. This is what we want to get. F equal to, right? But then I think it's the other way now. The composition is phi of a of fz is for. So let's see whether it's all right as it is or. So you will get phi a inverse of this. So we want to get z, not phi a inverse of this, but phi a inverse of z, right? So I think we will have to take f inverse there. If you take f inverse here, then what happens? If you take, right? Only then you will get 0 to 0. And then, see, do you see what the point is? As it is, we are getting, the way we wrote things down, we are going to get what? This is phi of a inverse. Of course, instead of a, you will get minus a, that's fine. But this factor will come in the Mobius transformation. That's not what we want. Of course, it's all the same, but what? Of e power a alpha z. Right? Or phi of minus a of e power a alpha z. Whereas what we want is e power a alpha outside, right? So we have to tweak things a little to get the correct form that we had written down earlier. There is nothing wrong with this. You can also describe automorphisms of D of this form. So what you want to get actually, f is equal to e power I alpha phi minus a. This is what we have to get. We are getting the composition other way. So what is the change that you have to make? So if you want to end up this way, so let us just to think in terms of operators. Suppose this is rotation by alpha, okay? So what we want is to get f this composed with rotation through alpha. What we get here is so we are getting the other way. So replace f by f. So if f is this, f inverse is going to be phi of a r minus alpha. R alpha inverse is r minus alpha. So this is the way we have written down things down there, right? No, wait. What is this? This is, yeah, this is what we have. What you want is this. So apply phi a and then multiply by this. Okay, right? This is what. So if f inverse is. So if you replace f by f inverse, I think things are all right. Right? If you have f inverse here instead of f, you will have f inverse is this. So f will be inverse of this. So r of minus alpha, alpha or minus alpha doesn't matter, times phi of a. Yeah. So I think that will be all right. No, so keep this as it is. Don't change that. Hmm. Yeah. Okay. Yeah. Otherwise, you want 0 to 0, right? So this is fine. So phi of a into f inverse is this. So that is f inverse equal to phi of minus a or phi a inverse if you want, doesn't matter. R alpha, where R alpha is rotation by alpha. So f is equal to, so rotation through alpha, the inverse is rotation through minus alpha, right? So instead of alpha, we are getting minus alpha. Anyway, that is not a serious thing. It doesn't matter whether you write this way or that way. So the automorphisms of the unit disk are just the, the Mobius transformations of the form phi a multiplied by something of modulus 1, right? Of course, if you remember, I had mentioned sometime earlier that the automorphism group of the unit disk is the group SU11. So you can see that SU11 is same as this group of all maps of this form. Of course, in general, the task of given any domain, connected domain, the task of determining the automorphism group of the domain is not an easy task, right? For a unit disk, it's almost an easy consequence of the maximum modulus theorem and the Schwarz lemma. Now, once you have it for the unit disk, you will have it for the upper half plane because the upper half plane and the unit disk are isomorphic, analytically isomorphic via the Cayley transform, as I mentioned the other day. But in general, say even if you take an annulus, for example, finding all the automorphisms is not a trivial task. Okay, so now we can come back to Schwarz lemma and see what happens if you don't assume F0 is 0. So there is a more general lemma which drops that condition. It's called the Schwarzschild lemma. F from D to D, analytic. Then which way you want, right? Doesn't matter. Let's write all F to the one side and all the other things to the other side. for all z and zeta. If you take zeta equal to 0 and assume that f of 0 is 0, then what are you getting? So this is f of z, right? This is 0, so this is 1. So on the left hand side, you get just f mod fz. On the right side, you are going to get just mod z. So when you take zeta equal to 0 and assume that f of 0 is 0, you get back the Schwarz lemma. By the way, the looking at those 5 A's that we looked at, you see that the automorphism group acts transitively on the disk. Which means what? Given any 2 points in the disk, you can find an automorphism which takes this point to this point. Right? Given Z1 and Z2 in the unit disk, there is an automorphism which takes Z1 to Z2. Why? These 5 A's are automorphisms which take any point to 0. Any A to 0. Right? So, for any point in the unit disk, there is an automorphism which takes that to 0. So, go this way. If you have 2 points, there is something which takes this to 0, and there is something which takes this to 0. The inverse of this will take 0 to the other one. So, go this way, you get something which takes this to this. Right? So, you should write out and see, all this dance, is not a proof. So, you should actually write it out and see. So, if A and B are 2 distinct points, not necessarily distinct, of course, the same as the identity map is there. Okay, so 2 points on the unit disk. So you take phi A and phi B. Phi A of 0, A is 0. Phi minus B of 0 is B. So when you compose, you get something. It takes A to B. That's all. So automorphism group acts transitively only. Right. So it's much more than transitive action, but we will not worry about it. Okay, so you can note that anyway, at least the statement. Automorphism group acts transitively. Now, all that you have to do to get this is to apply the Schwarz lemma for a suitable function. That's all. So I'm not going to give you the details, but I'll check. I'll give you the statement. You check that statement. Okay. Of course, you have to check whether it's correct or not. So, what you have to check is whether this maps 0 to 0. Okay. What does phi zeta do? Phi zeta takes zeta to 0. Okay, no, Oh, you want to start with 0, right? We want to see what the image of 0 is. The image of 0 under phi zeta um, minus zeta, right? Phi of a, z minus a by something. So if z is 0, it's minus a, and minus zeta here. Or maybe you should take minus zeta here. Okay. Minus zeta. Take, so this 0 goes to zeta, right? And so f zeta, and f zeta goes to 0 in this. Right? I think this is fine. Just check that this g of 0 is 0 with this, and then apply Schwarz lemma. And then, of course, you have to transpose some things to this side and so on. So you have to do the computation there. Of course, as I said earlier, there is a vast generalization of these things to what is called the Alphonse Schwarz lemma. It contains all this, but we'll not discuss that. Geometric lemma of Alphonse.